It looks like
All right, I'm going to go ahead and get started. So welcome, everyone. My name is Josh, and I'm a statistician at SEDAD, part of UVA. And I've been asked to talk to you about exploratory data analysis. And I know that on Monday you had a training about ggplot, specifically making box plots and histograms and a few other methods for visualizing data. So this is not going to focus on actually making those displays, which you now have all learned how to do very well, but more on the way you should be thinking about approaching data analysis from a philosophical standpoint and from iterative nature of critical thinking and analysis leading to insights that inform your modeling, letting you look at structure of your data and your residuals and using that to give you insights on how you should continue to iterate to reach new conclusions and get new insights into your data. So this, I want to mention, is based largely on work that Vicki Lancaster, who's also with our lab in SDAD, she's put together a workshop on this, so I borrowed very heavily from that here. So I want to start off by talking about data analysis in general. So data analysis, it's not a case of simply applying, some choice of model from your tool belt of statistical models to a problem. It really is this critical thinking assignment. You have to make critical assessment, explore the data, test it, and via models, and then evaluate that. So it's a domain that requires intelligence and care and the application of knowledge and expertise about the data. It's a challenging and demanding discipline, and it's a discipline that is continuing to evolve, and it evolves as computing methods extend our ability to do analysis to larger data sets and higher dimensions, which in turn leads to the development of new statistical methods of inference. So what do we mean when we say exploratory data analysis? So EDA is a process that uses non-inferential statistics, such as graphical methods, to gain insight into a set of data. So it characterizes the notion that statistical insights and modeling are driven by data. So I think that the main contribution of EDA is a philosophical one as a guide to analysis. So it's advocating for exploring the data for patterns and relationships without requiring you to come in with any prior hypothesis, but rather letting that inform what your hypothesis will be. And if you think of your data as a story written in numbers, then EDA is also the process of translating that graphically to one illustrated with pictures. So what do we use EDA methods for? To isolate patterns and relationships, to uncover unexpected behavior in the data, to confirm or disprove our assumptions about the data or our assumptions about statistical modeling techniques, and to reveal information. And in particular, EDA is important because most of the classical procedures that we use are based on assumptions about the characteristics of a variable. And the validity of the tests that we're doing depends on making sure that those assumptions are met. So the graphical methods of EDA, they provide the diagnostic tools for confirming or disproving whether or not our modeling assumptions are met, and when they're not met, for suggesting how we might go about correcting them. So I want to start by, this is the naive non-EDA approach. Let's take, quote, some data and run a one sample t-test and test whether our population mean is equal to 1. And we run that and we get our test statistic and we get our p-value. And what's our result? Our p-value is greater than 0.05. So we failed to reject the null hypothesis. So the end, question mark, are we done? Well, we missed a very important first step before we even consider doing any statistical testing, which is to actually examine our data. So if we had done a few plots on the data first, here we see some examples of plots for one continuous variable, a histogram in the upper left, a box plot in the upper right, our smooth density plot, and our quantile plot to check normality. And these are all pretty hard to read right now because we have one potential, quote unquote, potential outlier, one observation that's out at over 1,000 here in our data set. So let's look at these same plots after removing the outlier. So if we can make the assumption that the outlier is due to an assignable cause, such as, for instance, a data entry error, and then we correct that, then we can see these same plots. And now we are, seeing that our data are approximately normally distributed. And so when we're looking at a one sample t-test, in this case, the t-test makes the assumption that our data is approximately normally distributed. So now we are not violating the assumptions of that test. And we can go ahead and do that, and we can reach the conclusion that, yes, the population mean is significantly different from 1. So a great quote from this book that is the follow-up to Tukey's seminal work on EDA, which is, there is no single statistical tool that's as powerful as a well-chosen graph. So I want to give some historical background to the development of exploratory data analysis. So the very first published presentation in 1771 was a book by Tukey, and the sort of definitive account of this is the 1977 book on exploratory data analysis. And it really deals with what at the time was a tension between two opposite points of view. The view that hypothesis must not be influenced by the data, that we should go in knowing that we are going to do this statistical test and then let the outcome of that test stand on its own as a complete result. And then the other view that Tukey advocates for, that you need to look at this data in an exploratory way, graphically, prior to inferential analysis, to understand what type of model, how rich a model the data can actually support. So it's really dispelling the myth that we're not allowed to look at the data at all prior to modeling. And Tukey identifies 4 themes that run throughout and reoccur throughout exploratory data analysis. And these are the ideas of resistance, which calls for identifying cases that are extraordinary and then setting them aside or otherwise downweighting them in your analysis. Residuals, which is the idea that you summarize the patterns that you found so far in the data, and you subtract that summary from the data to reveal departures and additional patterns that you couldn't have seen before. And so exploratory data analysis works with residuals to refine or extend the models that you fit into the data. There's the idea of re-expression, which is using mathematical transformations to simplify the patterns in your data. And we do this because analyses are more useful and more productive when we've transformed data to agree with the basic assumptions of the models that we're using. And frequently throughout all of these processes using graphical displays so that we are always in contact with the data, the residuals, and the summaries. And we do this throughout to reveal unexpected behaviors. So this approach does not end with a hypothesis test. So the effective way that you do EDA is iteratively. So you run through these to find and summarize patterns, and then we use the understanding that we've gained to take a deeper look and go back through this over and over again. So I'll go into some more detail on each of the four themes. So when we say resistance, a resistant measure, this is a property that is relatively unaffected by the presence of outliers. So an example, a resistant measure of location would be the median. A resistant measure of spread would be the interquartile range. Generally, we say that a summary statistic is resistant if it's insensitive to any small change in a large part of the data and insensitive to any large change in a small part of the data. So the resistant summary statistics have the property that they pay attention to the main body of the data and they give little attention to the outliers. So when we are looking at structures and patterns in our data, it's useful both to summarize the main body of your data and to identify outliers. So especially the construction of box plots is useful at doing both of those things. And just to look at the example before of our data with an outlier and with the outlier removed, we can see the difference between a resistant and a non-resistant statistic. So for instance, we look at the mean with the outlier is nearly 12, and when we remove it, it's close to 2, whereas the median is not sensitive to this outlier. It remains largely unchanged when we take away the outlier. One note is that we mean different things when we use the language robust versus resistant. So in statistics, saying something is robust, it's applied to an inference procedure, and it's saying that your procedure is stable when the model assumptions are violated. So for instance, the one sample t-test, we would say it's robust to the assumption of normality. That means that that t-test is in doubt only when there are severe outliers or departures from normality. Whereas resistance, we say that the statistic is stable under contamination of the data values. So the median is a resistant estimator of location. So it's sensitivity to model assumptions versus sensitivity to data. When we talk about residuals, so exploratory data analysis, we characterize statistical modeling as a decomposition of the data into structure and noise. So, roughly speaking, we say that data is equal to some pattern or some fit plus the difference between the data and that pattern, which we call the residuals. So We then examine the residuals to identify structure, and then we can attempt to capture that additional structure that we see and move it into the fit. So the fitting process is repeated and followed by subsequent residual analysis. So it's, it has its roots in the general statistical paradigm of you partition variability into explained and unexplained variation. And then you're doing that in an iterative process. I want to just show one example of when residuals are, violating your modeling assumptions. So this is an analysis using ANOVA, or analysis of variance. So that's a statistical method that you are describing analyses of data that involve two or more factors, and you have one or more observations for each possible combination or levels of across all those factors. So this particular example is a 2x2 factorial design for men and women who are sighted or congenitally blind. And in this experiment, subjects were asked to detect a change in weight pulling on a ring wrapped around their finger as the weight slowly increased over time. And so some assumptions that need to be met when you're doing analysis of variance are that your residuals are normally distributed and they show constant variance. So in the leftmost plot in this initial analysis, using the weight as a response, we can see that there's this fan shape to the residuals, right? So the variance is increasing with the predicted value. And we can see that there's this curve, so there's evidence of nonlinearity and heteroscedasticity in your residuals, indicating that you violated the assumptions of the ANOVA. And so what are our options when the residuals show a violation of the assumptions? Well, we can decide to re-express variables to mitigate the violations of these assumptions. We can choose to set aside outliers that we've identified using the residuals. Or if we have the option to, we can introduce additional variables that are suggested by the residuals. And so here, if we look at the rightmost plot, this is that ANOVA fit with a different response. And an additional variable was incorporated that was present in this experimental data set, which is the rate at which the weight was increasing, used to change the response to units of time. And additionally, the data is also re-expressed on the logarithmic scale. And so, after making these transformations, researchers found that this fixes the problems with the analysis, the problems of the heteroscedasticity and nonlinearity of the residuals. So the philosophy of EDA is that any analysis of a set of data, it's not complete without carefully examining these residuals and making sure that your assumptions are met. And resistant analyses provide a clear separation between dominant behavior and unusual behavior in your data. Residuals will let you identify any drastic departures from that pattern, as well as seeing if you just have random fluctuations in your data. So the next theme is re-expression, and this involves the question of what scale would help to simplify the analysis of the data. And so really what re-expression is, it's the application of a mathematical function, such as a square root or a logarithm, to each value of a variable. And so the transformation that you're doing here smoothly changes the positions of the data with the goal of simplifying the analysis. And sometimes people have the attitude that transforming the data is somehow wrong and that you have to work with the data in their original scale. But this is an attitude that may cause you to miss a lot of important features in your data. And in fact, we see that, you know, there's some scales we can think of just in everyday use that are on a transformed scale, such as like the Richter scale, where you're measuring earthquake motion of the earth in logarithmic units. And decibels measure sound pressure logarithmically. So re-expression is very common in social sciences. And what are the advantages of doing that? You know, the distribution of the data and the residuals can be made more symmetric, can be made more nearly normal. It's possible that an alternate scale can help to facilitate your interpretation of the results. The variances of several groups that you want to compare can be made more nearly equal. You can correct for heteroscedasticity across a continuous variable as well. You can ensure that the relationship between two variables can be made more nearly linear. So these are all things that re-expression helps us to achieve. And it most often comes in the form of power transformations together with logarithmic transformation. So here on the right, you know, we have a little diagram that is the ladder of transformations. And it's expressed in terms of, you know, p, the power that you're doing this transformation. So p equals 2, it corresponds to the squared transformation. P equals -1 would correspond to the reciprocal, taking 1 over the data value. And p equals 0 is what corresponds to a logarithmic transformation. And actually, we can combine these and fill in the gaps by treating the exponent as a continuous variable that's varying from positive to negative using what's called the Box-Cox family of transformations. And I've given the functional form of that there. So it varies over the continuous parameter lambda, which is like the power here as we're moving up and down the ladder. And so, for instance, we may want to transform a continuous variable to make it look normal, so it can achieve normality and perhaps satisfy the assumptions of a regression model, for instance. So a standard normal quantile plot, that's where we're plotting the quantiles, the empirical quantiles of the data on the x-axis versus the theoretical quantiles of a normal distribution on the y-axis. So when the data is normal, it should fall right on that line of x equals y. And so we can, you know, sort of see the effect of plotting a transformation of a data set as we're moving, in this case, down that ladder. And when we do the log transformation, things are looking approximately normal. As we're moving down the ladder, things are looking more and more right skewed. And you can see in the quantile plots that we're deviating more and more from the assumption of normality on this tail end, this curving up. So our last theme, displays. You know, they meet the need to see the behavior of the data, to reveal unexpected features in the data, such as outliers, to confirm or disprove assumptions, such as the distributional assumptions of the statistical tests that we're doing. And Tukey argued that good graphical methods should allow unexpected values to present themselves so that we can identify them and expand or modify our models to account for them. Let's see. So I want to pause for a second and see if there are any questions at all from the group chat. So this has gone pretty quickly. So this is actually going to be the final example that I talk about. And this is, I think, a very cool example that illustrates the power of taking a graphical look and critical thinking strategy to your data analysis. And this is from the Los Alamos National Lab. This is their environmental restoration project. And so this is looking at areas that are contaminated by nuclear waste, by chemical waste. And so they looked at an extensive site characterization using surface soil samples to look at the presence of uranium in the soil. And so these were collected and compared to background data. And in particular, they were collected from this largest zone of contaminants and analyzed for elemental uranium. And so here's the result of 145 different soil samples that were collected from around this site. We can, just looking at some visualizations of this in terms of a histogram and a box plot, looking at the distribution of the uranium concentration. And so what leaps out here in the histogram is that there's this bimodality. And so we would, having identified this, we would seek to try and understand what are the possible hypotheses that could give rise to this, one concentration of relatively low uranium and one area that has a concentration of high uranium. Well, I say area, but that's one hypothesis, is that they differ spatially because of, maybe because of historical disposal operations. It might be due to geology issues, due to different rocks causing different background concentration distributions. It might be due to chemistry issues. If different analytical methods are used to actually analyze the soil, you may have issues with compatibility between the two different ways that data were analyzed. Or it may be due to how the sample was actually collected. If it's due to different sampling methods, a different field team, or other compatibility issues with that. And so, this suggests, our EDA suggests a further look at our data. And in fact, in this case, there were two different analytical techniques that were used, which are noted here by KPA and ICP-MS. And so we can see that if we look at the histograms of each of these two separately, and actually in the plots right below those histograms, we see the spatial distribution of where those sites were performed, and then a box plot that summarizes those. But we can see that these two peaks sort of neatly decompose the two peaks in our bimodal distribution that we saw earlier. So in this case, we saw that the problem was a lack of comparability due to the inclusion in this collection of two very different analytical methods. And so this actually brought about a change in policy at Los Alamos, where the method that was older and slower is no longer being used for uranium analysis going forward in this project. So I want to give a final conclusion slide here. And I've done this sort of in a checklist that is good for you to go through as you're approaching a data set for the first time. So start by making displays of individual variables of interest and identifying any special issues with them, be that they're highly skewed and might benefit from re-expression. Maybe you detect the presence of outliers in them as you're making these plots. As you're modeling them, check any models for the data by examining the residuals and using that to suggest changes or extensions to those models. Be aware throughout this process of the opportunity to re-express variables to simplify models or satisfy assumptions, and be willing to remove or fit special terms for outliers or influential cases. And then iterate, then go back to the start and do this again with the new insights that you've gained. And this will help you to refine your research question. This will help you to refine the conclusions that you get, suggest new models that you might want to fit to your data. So when you just apply a statistic primarily to test a set hypothesis that you have going in, what you often get is a sort of false sense of completion about your work, right? So what you've done is you've stated and tested the hypothesis, and you've reached a conclusion, and there's a sense of finality about that. But the philosophy of exploratory data analysis, you don't adopt this attitude. You iterate, and there is no natural stopping place. So the power of EDA is that we always leave open the possibility that new data or new understandings can lead us to modify our analysis or develop it further. And that's all I have. So if there, I'll leave some time for any questions that you guys have in the group chat. And if there are no questions, then I will let you enjoy the rest of your afternoon and have a good weekend.
Thanks, Josh.